Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi and today we are going to discuss about the module Rheology, casting and plastic forming, and this is from the paper Processing Ceramics. So students, let us see what we are going to learn in this module. So first we will be discussing about rheology of ceramic suspensions. Then we will be discussing about viscosity of suspensions and slurries. And lastly, we will discuss about ceramic forming by casting. So before moving in this module, we have discussed in the previous module regarding dry pressing. So dry pressing is a common method to form a ceramic shapes. So in this case, the dry powder containing small amount of binder is used. The ceramic shapes can also be produced from several other techniques. One of them is casting process, in which slurry of ceramic particles is used to cast the required shape in porous mold. The technique that can produce complex shapes as well as massive refractive shapes is this process, and it is also used for advanced ceramic because of the ability to control the agglomerates and uniform mixing of all the additives. So other than that, there are various techniques available for shaping it from a paste of ceramic powder, and these techniques include extrusion, injection, molding. So these forming techniques are discussed in this module and we will be discussing one by one. So first we will talk about rheology of ceramic suspensions. Rheology concerns itself with the flow and deformation of materials. It is of great importance in the casting process. The parameter most commonly measured in the rheological measurements is the viscosity. In ceramic processing with suspensions, slurries and paste, it is essential to know the rheology. Rheology is important in processing as well as in operations such as storing, pumping, transporting, mixing, etc. of a ceramic system. A ceramic system such as suspension or slurry is a complex system. The rheological behavior of such a system depends upon the particle size, concentration of the particles in the suspension, the interaction present between the particles and other factors. So there are different types of rheological behavior in ceramic suspension. The viscosity of a suspension is measured using viscometer. The shear rate used for measuring the viscosity can be varied. For a given shear rate, a shear stress is applied by the viscometer. The ratio of the shear stress to the strain rate is called the viscosity, or it is given as tau is equal to eta gamma dot, where tau is the shear stress and gamma dot is the strain rate. It should be noted that the viscosity eta is generally a function of the strain rate except in one case which is discussed in the next slide. Now, the rheology of ceramic suspension can be Newtonian type also. So, the Newtonian viscous behavior of gamma dot is discussed in this slide. So, when the shear stress is directly proportional to the strain rate at all the strain rates and the constant of proportionality, the viscosity does not change with the strain rate. Then, the behavior of the fluid is called Newtonian viscous behavior, which is shown in this figure. In this case, a plot of strain rate versus stress is a straight line. Such behavior is found in pure liquids and in dilute suspensions. So the next behavior is pseudoplastic behavior. In this case, the viscosity decreases with increasing strain rate, that is the apparent viscosity, which is given as eta A, that is apparent viscosity, is equal to tau divided by gamma dot. So this apparent viscosity decreases as the strain rate increases. A plot of the strain rate versus stress has a decreasing slope with the increasing strain rate as shown in this figure. This behavior is found in liquids with long anisotropic molecules, suspensions with long particles, and in flocculated suspensions. As the shear stress increases, the molecules or the particles get aligned in the flow direction and the strain rate increases. This behavior can also be described by the power law, which is stated as tau is equal to k into gamma dot to the power n, where n is always less than 1. Now the next behavior is dilatant behavior. Here the apparent viscosity, that is eta A, increases with increasing strain rate so that the slope of the strain rate versus shear stress plot increases with increasing strain rate, as can be seen from this figure. This behavior is characteristic of concentrated deflocculated slurries. With increasing strain rate, the particle interference increases, leading to an increase in the viscosity. This behavior can also be described by the power law, which we have mentioned earlier, that tau is equal to k into gamma dot to power n with n greater than 1. In all the cases which we have mentioned earlier, sometimes the plot does not start at the origin but starts at a finite value of the shear stress. That is, the strain rate remains 0 until the shear stress is increases above a certain value. This value of shear stress is called the yield stress. Now the terms comes thixotropy. What is thixotropy? Thixotropy is the decrease in viscosity with time while stirring at a constant strain rate. An example is flocculated suspensions, in which the flocks break with time during stirring. And if the flock break down increasingly with the time, then the viscosity will also decrease, as can be seen from this figure. Viscosity of suspensions and slurries. So in this slide, we will be discussing about viscosity of suspensions of dispersed colloidal particles and viscosity of concentrated suspensions and slurries. We will first talk about viscosity of suspension of dispersed colloidal particles. In this case, a relative viscosity eta R can be defined as the ratio of the viscosity of the suspension to that of the pure liquid, and it is given as eta R, that is the relative viscosity, is equal to the ratio of eta suspension and eta liquid. Then for a very dilute suspension of non-interacting spheres in a Newtonian fluid, the relative viscosity is given as eta R is equal to 1 plus 2.5 times F, where F is the volume fraction of the particles. The increase in the viscosity with increasing F is caused by the dissipation of energy as the liquid moves around the particles. This equation is known as Einstein's equation. Now, if we talk about non-spherical particles, then the constant in this equation, that is eta R is equal to 1 plus 2.5 F, the constant is more than 2.5. It will not be 2.5. Now, we will discuss the second case, that is viscosity of concentrated suspensions and slurries. The equation which we have described above for relative viscosity, this equation is valid for dilute suspensions. When the concentration of particle is greater than 5 to 10%, the interference between the particles causes the viscosity to increase rapidly. The behavior of the concentrated suspensions and slurries can be described by an empirical equation which is given as eta r is equal to 1 minus F divided by FCR to the power K times FCR, where FCR is the critical packing factor at which the flow is blocked and K is a parameter. The behavior can be seen in this figure. For an aqueous suspension of latex spheres of diameter 0.7 micrometer, it was found that K is 2.7, FCR is 0.57 to 0.68 depending on the shear rate. The same expression describes the behavior of slurries which may have particle size distribution ranging from colloidal to a coarse particles. So a simple equation can be eta r is 1 minus F to power minus K. This equation is used sometimes. In this equation, K is equal to 3 for a continuous distribution of sizes that pack more efficiently. K is equal to 21 for coarse particles of uniform particle size. Now, as I minus F is less than 1, eta r is higher for the later case. A diluent behavior can also be observed in concentrated slurries due to mutual particle interference, especially in the case where a high repulsive interaction is present. A dilatant behavior makes the pumping and handling of the slurries difficult. Now we will discuss about the effect of the state of dispersion on viscosity. The viscosity increases as an initially dispersed systems become more and more flocculated. An example is shown in this figure where the viscosity is plotted as a function of pH. Near the isoelectric point, the aggregation of the particles occur. The increased torque required for this causes an increase in the relative viscosity. The flocculated suspensions can be pseudoplastic as an increasing shear rate breaks the flocks to a great extent. It can also be thixotropic if more and more flocks break with continued stirring. The apparent viscosity is therefore very much dependent upon the shear rate and time. Now we are directing towards the ceramic forming processes using slurries and paste. There are many ceramic forming processes which starts with ceramic slurries or paste. These are casting, filter pressing, extrusion, injection molding, etc. We will discuss all of these one by one. So here comes slip casting. Slip casting is a technique used for manufacturing chemical porcelain ware, refractories having complex shapes or massive in size, sanitary wares, porous thermal insulations, bone china and so on. Slip casting is also used for high performance ceramics with complex shapes because of the ease of controlling the agglomerates, better mixing of the additives in the slurry and low inversion. So the process essentially consists of preparing slurry of the ceramic to be used and pouring it in a porous mold. The liquid is slowly sucked out through the pores of the mold due to capillary action to the external surface where it evaporates. A cake is formed adjacent to the internal surface of the mold and the remaining slurry can be poured out of the mold after the required thickness of the cake has formed. So this complete process is called drain casting. So we will start with slip casting. Alternatively, the slurry is not poured out and the casting process is not allowed to proceed to completion, at the end of which a solid body with a pipe running through its center is produced. This is called solid casting. The two types of casting are illustrated in these figures. After the casting process is complete, the separation of the cast from the mold occurs due to the drying shrinkage of the cast. It may also be affected by blowing air through the mold from the outside. The casting time may range from 1 hour for a porcelain part within a thin wall to several weeks for a several refractory cast of thickness of 30 centimeter. The casting time may be reduced by pressure casting or vacuum casting. The slurry of slip casting can be formulated very carefully to achieve several objectives. These include: the casting rate should be reasonably fast, the cast should have adequate strength for handling subsequent to drying after removal from the mold. And another is the level of porosity in the cast should be as desired. And the last one is the cast should have uniform thickness. Now there are some considerations which we should take into our mind in slip casting. So some factors which are considered while formulating a slurry for slip casting are: first, a large amount of fine particles in the slurry will produce a cake that has a low porosity, and so the casting rate will be slow and non-uniform. To avoid this, the slurry can be partially flocculated. Second, if the viscosity is too low, such that the particles would tend to settle to the bottom and the available casting time would be small, in slurries with a high viscosity, larger particles can be accommodated. Third, it is desirable to keep the solid loading in the slurry as high as possible so that less liquid has to be removed. The solid loading depends on the thickness of the double layer around each particle. In high, deflocculated slurry with fine particles, with each particle having a double layer, the particles cannot be brought closer than a certain distance, and so the solid loading is limited. Fourth, for drain casting, the viscosity should be low, that is less than 1 Pascal second, while it can be greater than 100 Pascal second for solid casting. And the last one is the binders are used to provide strength to the cast. Most often, clay is used as a binder. Organic binders of medium molecular weight or inorganic binders are also used. A mixture of binders can also be used instead of clays. The mold is commonly made from plaster of Paris, that is PP, which is partially hydrated calcium sulfate. On addition of water, it gets hydrated to gypsum, and the equation is written as follows, and the equation is CaSO4.5 H2O plus 1.5 times H2O gives CaSO4.2 H2O, which is gypsum. The gypsum forms in the form of interpenetrating needles and plates and produces a mold with adequate strength. The water to PP ratio according to the above reaction is 18.6 by 100. So a range of 60 by 100 to 80 by 100 is used to produce the mold to give adequate porosity. The variation of the strength of the mold and its water absorption capacity with water to plaster ratio is also shown in this figure. The liquid being removed from the slurry has to pass through the cake which forms on the wall of the mold. The cake acts as a filter. The uniaxial flow rate through a filter is proportional to the difference in pressure, that is delta P, across the filter with thickness L and cross-sectional area A. So the equations become Q is equal to KdA delta P divided by L, which can also be written as KPA delta P divided by eta L, where Kd is the DRC permeability coefficient and eta is the viscosity of filtrate. Moreover, Kp is the specific permeability. For the filtration through a cake, one gets the formula as L square by T is equal to 2j Kp delta P divided by eta, where L is the thickness of the cake produced in time T, J is the volume of the cake per unit volume of the filtrate. This equation shows that the thickness of the cake increases as the square root of the time of casting, and it is similar to the diffusion equation, which is L is equal to D times root T, where L is the thickness through which the diffusion of the species takes place in time T and D is the diffusion coefficient. Now the next process is tape casting. The tape casting process is used to produce thin means less than 1 millimeter. So to produce thin ceramic sheets. A slurry made in organic solvents like trichloroethylene or ethanol and containing substantial amounts of organic binders, example methadone fish oil, polyethylene glycol, etc., is poured over a flat surface and a sharp blade with a small clearance positioned over the surface is moved along the surface, which is seen in this figure. This produces a thin layer of constant thickness. The thickness of the layer can be controlled by controlling the gap between the blade and the casting surface. Upon drying, the sheet becomes leather-like and can be slit, punched, etc. before sintering. This process is used to produce multi-layer capacitors, substrates of electronic packaging, etc. Now we will discuss the plastic forming. So the mixture of clay and water produces a plastic mass, as we all know, which can be shaped by deforming into the desired shape. Processes like extrusion, plastic pressing, jiggering have been traditionally used to shape clay bodies. A plastic mass can also be produced by mixing any ceramic powder with clay or organic binders, and the same process can be used to produce the part of that ceramic. So we will first discuss the extrusion. In extrusion, the plastic mass is forced through a rigid die having a desired cross section. The process is used to produce long section with a desired cross-sectional shape. The products made by extrusion include a variety of refractory and porcelain products of complex shapes such as hollow surface tubes, honeycomb catalyst supports, transparent alumina tubes for lamps, flat substrates, etc. So the two types of equipments which are used for extrusion are discussed below. In one, the plastic mass is pushed by a piston inside a barrel and through a die, which is shown in figure A. This is a batch process in which feed material is fed intermittently, and in the second type of equipment, the feed material is fed and carried in the barrel by a rotating screw called an auger. This is also shown in figure B. The arrangement of auger extruder is shown in this figure also. The pressures used in a piston extruder is about 4 megapascal for porcelain bodies and about 15 megapascal for organically plasticized bodies. This can be compared to the pressure of about 200 megapascal which are used in dry pressing. Now the next is injection molding, which is a type of plastic forming. As mentioned earlier, in injection molding, a molten thermoplastic heavily doped with ceramic powder is injected into a die as shown in this figure. It is a rapid process and can produce complex shapes with thin sections. So in injection molding, the thermoplastics are preferred over thermosets because of the factors such as storage stability and reusability of the scrap. Two types of thermoplastics are generally used. One is called minor binder, which during the post-forming removal of the polymer burns out earlier and provides pore channels for the escape of the major binder, which burns out later. In addition to the binders, a plasticizer, or we can say lubricant, and a surfactant for particle wetting are also used. Some of the examples of major binder are high molecular weight polythene, and the example for minor binder is paraffin wax, etc. The temperature used during injection molding is about 125 to 150 degrees Celsius, higher than the temperature Tg of the major binder. The pressure used is 30 to 100 megapascal, and during injection molding, maintaining suitable temperature at each location is very critical process. The parts with complex shapes, dimensionally accurate and with smooth surfaces can be produced by injection molding. The tolerance is thickness, which is around 0.5 to 5 mm, and the holes smaller than 1 mm can be produced with a tolerance of less than 0.1 mm. So students, let's summarize what we have learned in this module. So first we have read about casting and plastic forming processes. Then we have discussed the first process, that is casting, where we have learned that rheology is very much important. Next, we have read about pseudoplastic behavior, in which the viscosity decreases with the strain rate, which is desirable for casting. And in slip casting, a slurry is poured into a porous mold made of plaster of Paris. A cake forms, which is stripped off and fired to yield the ceramic part. The process is used for complex and large refractory shapes, sanitary wares, and so on. So next we have discussed in extrusion, a paste of ceramic and binders is extruded through a die. Complex shapes such as honeycomb, catalyst supports, hollow tubes, etc. can be made. Whereas we have discussed also that the injection molding process is very much similar to that used in polymer processing. A paste of ceramic powder and up to 70% polymers is used, and thermoplastic polymers are preferred over others. Thank you.